Good evening, folks. I think you're already aware of the type of sessions that are happening. Well, in the first session, it was just the theoretical concept of machine learning, like what its types, supervised, unsupervised, reinforcement, and then we just went into like how can we directly use those models, pre-built models from scikit-learn and stuff. And I think you might have heard about all of these chat GPT and even image generators and all of these stuff. They are very interesting. They're very interesting and they work well, right? Well, how are they built exactly? What is the basic concept from which all of these are made up? A minute. Okay. Yeah. Yeah. So, like, what are the basic building blocks for all of these things? Well, we call them neural networks. Neural networks, they were made to replicate how our brain works. You know, artificial intelligence, like trying to mimic human intelligence, right? In the same way, these neural networks were made to mimic our brain neurons. Even their structure is very similar. Like they'll have, I think I'll show one example of neuron diagram. Mm, yep. See, mhm, yeah. So this have neuron looks. You can see all of these dendrites, right? They take information, processing is done over here, and they're passed on to the next set of neurons. In the same way, like very similarly, the neural networks in machine learning also works. These take the inputs like this one over here, and they're computed over here, and they're passed on to the next neuron. Here there will be another neuron connected. Like for example, in this way, one neuron takes the input, has its connections, moves on next neurons, and these are connected to the next ones. And this is like a single block of neuron. And here how it's done. Well, it's taking inputs and it's passing on to the next neuron, and we are saying that some sort of processing is happening in those each block. Well, what sort of processing is happening? What exactly are we doing? Well, these x is our input, um, and the connections between each block, this one, have a weight. They have some particular importance. This importance we calculate in such a way that um, by this complete accumulation of these weights, we can create a function. Yeah, we can create a function which maps our real-time scenario. For example, let's say that we are trying to predict a stock price. We are trying to predict the stock price based on how many sales have happened, the share, like how many stocks are available in the market, and at what price they are being sent. All of these are our parameters. On all these factors, our prediction will depend on. So all of those will be our x inputs. And now I want to give more importance to the fact that there are less number of stocks, less demand is there. So more people are trying to buy, but there are limited number of stocks. At that time my price will be higher. So for that particular input, for the how many stocks are available in the market, for that particular input my weight will be higher, my importance will be higher. And all these weights in the earlier stages were manually updated by humans, but later on we started using some algorithms to compute them. Well, all of this process takes a lot of computational power, and for that reason these weren't as widely used as, like we are using them at a larger scale, like this transformers and all other neural network stuff, deep learning. They need high computational power. For that reason we use GPUs, graphical processing units. But in the previous times we used to just use CPUs, and for that reason this AI rise has started happening. Now X is there. It's similar to what our linear equation looks like. Y is equals to wx plus b into 1. This bias can have other values too, and we are adding them up. So our input will be going in here. They'll be multiplied and summed up and passed on to the next. This is a particular, like this is a single linear unit. And see, for example, um, here the weights are 2.5 and the bias value is 90. So we are the quantity of sugar is 5, like 5 grams of sugar. I want to calculate how many calories it is. 2.5 into 5 plus 90, it's 1 or 2.5. Well, but in actual it might be something less. At that time these weights and bias will be updated so that I will have an accurate value for this calories. Okay, in this example, there was only one input. But in our previous example, in the case of stocks, we had multiple inputs, like the price at which is it is being sold, the number of quantities, and the number of customers who are willing to buy and stuff. In our own example, we have mineral crypto bros burning GPUs to mine crypto. Yeah, yeah. Even they are using. Okay, that is it. Sorry, got distracted. Okay, in our previous example we had three inputs, but in this particular example only one is there. Well, how will it work? Will it work for multiple inputs? Yes, it will work for multiple inputs. At that time we'll have multiple nodes to take inputs. Here we'll give one input, like three inputs, and they will be weighted. It will be in this form: y is equals to w naught into x naught plus w1 into x1 plus w2 into x2 plus b into 1. Okay, we are saying that these weights are the importance we are giving to this inputs. We want to we want to change our consideration, how much importance we give to input. But this bias value, it's not related to input. Then why do we have to change this bias value, and why do we even have to include this bias value in our uh, neuron? In uh, in a mathematical world, like for example in a we used to solve problem statements, like word problems. There used to be a scenario in which Raj buys 5 apples and he sells four of them, and we have to find the profit and stuff. All of these are scenarios created by humans. We create them in such a way that a perfect solution exists, but in reality there are too many factors to be taken into consideration. And all of these for example in the previous example, like we have taken in stock market, we took three parameters, but in reality it might change. It might be many more. Some random tweet by some random guy can also affect it. Even that is a variable, even that is a parameter that is affecting our prediction, affecting the outcome. All those values we can't take into consideration. For that reason we put a bias which is not dependent on input, which is like some sort of a general factor to make our neuron work in a generalized setting. Well, I strongly recommend you folks to what do you say, go through this link. I'll just put it in the comments. Yeah. So we can implement these neurons with PyTorch and with TensorFlow. In Kaggle, they provide us resources to learn machine learning and deep learning. In that particular notebook, they have given with TensorFlow. Keras is an API for working with neural networks. This is our model, what we are building. Keras is our package, and sequential. Like I'll show you. See, this is how normally our neural networks look like. The input layer, the output layer. There are other layers. There are hidden layers. We can add more hidden layers, and we can reduce those hidden layers depending on how many hidden layers we are using, and in each layer how many neurons we are using. Our functions differ. We'll get to that in our next topic. So see here, first layer is there, and second layer is next to it, and the third layer is next to it. They are in a sequence. All these inputs, for example, see here the inputs are going in this way. First from here to then here, then here. They're all moving in a sequence. So we are building sequential models, and for that reason we are hello we are mentioning sequential, and it takes a single input. So we are putting all of this in a list. Dense layer. What is a dense layer? I will get to it in the next topic. What dense layer is? Okay. Now we got a basic idea of what a neuron is. Well, are there a single type of like layers, or there are multiple types of layers? There are multiple types of layers. For example, this is a dense layer. In dense layer, each neuron is connected to every neuron in its previous layer. For example, let's take this blue one. It's connected to XO, X1, and bias. And this one is connected to again XO, X1, and 1. Though these things are connected to the same nodes, okay, though these things are connected to the same nodes, these blue, like these lines, as I've already told you, we think of these lines as weights. They have some value. These will be different even though they are connected to the same inputs. And in our previous notebook, we have seen that these are nothing but linear equation, like wxo plus w1 x1 plus w2 x2. Well, if they are same, why can't we just write a linear equation, or why can't we just use linear regression? Why do we have to use neural networks? How are they different from linear equation? These activation functions makes the difference between our linear models and neural networks. There are few types of activation functions. The rectifier function. What this rectifier function does is, if the output at a neuron node, that node value is less than 0, it considers it to be 0, and if it's higher than 0, it takes that value. There are also other ones like a linear one. I think this guy did not mention here. I'll show you. Hmm, okay, where are the graphs? Okay, now this is a sigmoid function. What it does is, whatever the input which we give, this x is our whatever the value which we get out of a neuron at the end, this plots them onto the sigmoid function. Like if my value is 2.5, it goes straight like this, and what is its equivalent value on y? It's somewhere around 0.9. It gives 0.9. Well, what if my uh, output of neuron is 10? straight, draw a line, goes back, it's nearly 1. What this segment function does is it maps all our output values of a neuron between 0 and 1. In case of like if you are trying to classify an image as an object, you want to find the probability lies between 0 and 1, right? In such cases segment works very good. And the next one is tanh function, and as previously shown, relu function is already shown in over here, no, over here. And we have softmax function. There is also a linear function in relu function. All these values are all the values below 0 are considered as 0, right? In linear function they're not, it directly takes those values. Well, um, in our previous discussion, like in our previous notebook, I've told you that it's a sequential model. Each layer is connected to the next layer. How are they connected? They are connected in this way. Now our input x naught x1 1 goes to the first node. Half x naught w naught plus x1 w1 plus 1 into bias 1 b1, and then x naught w10 x1 w11, and then bias is computed over here. All of these computations are done in each particular neuron, and they are again interconnected with the next layer, and at the last they are given to this activation function, our linear activation function. Here there are two sequence, like two dense layers in between input and output layer. Well, in the same way, this is our single hidden layer, this is our input layer. Well, how can we say that it's our input layer? We mention the input shape over here, like how many input values we are taking, and then this is our output layer. Do try out the notebooks. Well, we have been continuously saying that these weights, they play a very important role in calculating the y value or the output value. And we also told that we need not manually update these values. These values are computed. Well, how are they computed? How are they adjusted? We use loss functions. I have already told about loss functions in the previous sessions. Well, we predicted a value and we have the actual value. We find the difference between these two to know how much we are wrong. Only when we know how much we are wrong, we can make adjustments so that we can give more better results. And this wrong value is calculated by our loss function. For example, these are the actual values. Let's take this. It's a case of a linear regression problem. We are trying to fit this line to these points. These are our actual values, and this blue line is the loss. We compute we square these loss, and then we add them to find out how much we are wrong. In the same way, we calculate loss for our model too, our linear our neural network models. Okay, they did not mention it here clearly. Okay. Hmm. Okay, not in this. Yeah. So here we are calculating the value, and we are giving out the outputs, right? And we are also stacking like this. Now if my output is here, it's y, and let's say y hat is my predicted value. Like I find the difference between my predicted value and actual value, and I find out some error. Now I have to use this error to change all these weights. How will I do it? when we give a function, we want to know how much impact a particular variable is having on that function. We find its derivative. But in this function, in this equation, there are many variables. All of these weights are variables. They have specific value, and this specific value is causing, like, is contributing some amount to the error. So we find out partial derivative of that error with respect to each weight, and we subtract that partial derivative value from these weights, and we rerun this model on our training data. We again get some more error, and we repeat the same process. This calculation of partial derivative of each weight, like how much it's contributing to the error, we call it stochastic gradient descent. There is also other variations like batch gradient descent, which are and the math behind it is complicated and is not necessary for this session, as it's a beginner friendly session. That's how these weights are updated. Now I've already gone through this topic of overfitting and underfitting. Well, uh, see, now these are all my values, and my optimal or original function should be in this dotted line. This finds generalized, like, this works in almost all the general cases. Of course there are some outliers and some abnormalities which we don't consider, because if we consider and if we just remember, we can't apply them in the real world. But in this particular diagram, you see, I'm just drawing a straight line. My function value is correct only to these values. It is not taking consideration into all of these values. Then I'm completely wrong, because they are following a trend, but I'm not even considering this trend. It means that I did not train my model enough on my training data. And in this case, this black line is going through each and every um data point, every value. My training accuracy is very good, but when I am testing it on real life, like on other things which we like on other data which I have not used to train my model, it's doing very bad. It's like a day before exam, I have remembered every question, and I've gone to the exam and I've written, I've got full marks. And in an interview, and month later, or in an interview, or when I'm in my job, I have to apply that concept, but I don't know how to apply it. All I know is just I remember this thing. I don't know addition or like I don't know multiplication. I just know that 2 into 2 is 4. I don't know why it is 4, and I don't know what 2 into 3 is. I Because I did not learn the 2 like 2 table in this in this example. It's not learning the 2 table. It's just remembering the values. This is what we call as overfitting. Now see, uh, we are saying that we are using multiple layers. Well, how should we know the number of layers which we are using are good or bad? Are we wasting our computational resource by making too many layers, or by adding too many nodes? Well, this particular point over here is very important for that reason. Wider networks have an easier time learning more linear relationships. Like if my like over here, if my function is actually this, making more layers, sorry, making adding more nodes in that will be helpful. But if it's in this way, in parabola or hyperbola, then adding more layers will make it easier. See, wider means we increased here from 16 to 32 nodes, and in deeper we're adding layers. How will we this effect? I'll show you. And in underfitting and overfit, like underfitting and overfitting, How should we know like when my model is underfitting and when it is overfitting? When the model works very bad on training data, it means that it did not learn anything. Then we can call it underfitting. And when my model works perfectly on training data but works very bad on validation data, on data which it does not see, we call it an overfitting. Well, I want to know that when should I stop training? In neural networks, you make your model see the data many number of times, so that each time when it passes, the weights are adjusted and it gets better at predicting the values. But I should stop at one point of time. And epoch is epochs are the number of times our model sees the data. Now see over here, the underfitting. Okay, sorry. The validation loss is decreasing till over here, and then it started increasing. It means that, but look at over here. My training data decreased till here, and it went on decreasing. But my validation data loss is increasing. It means that my model is remembering. I don't want my model to remember the values. I want my model to work in a generalized scenario, in a real-time scenario. So I'll stop it over here. I can plot these values, validation and training loss, and I can with epochs, and I can see where it's performing well, and I can stop the training over there. Okay, this is how you have to make your model architecture. As I've told you earlier, it's a sequential model, so we give multiple layers and we compile it with optimizer. Optimizers are used to adjust the weights of these models. Like in this third notebook, where they have explained about stochastic gradient descent, these loss functions are used, right, to adjust the weights. These optimizers help in adjusting those weights. Now, yeah. Now we were talking about how the model works. If I increase the number of nodes in a layer, we call it wider. It works well for linear functions, but it does not work well for non-linear functions. Right? Let's put it to test. I'll just okay. There are supposed to be only two layers. I'll just put this in the comments too. Okay, a minute. Um, okay, this should be enough. Well, in these notebooks, we were building our um, models by code, but let's just see how they actually work. Now, see, this particular thing is not a linear function, because as you can see, these blue values are in the center and these orange values are on the outside. Whereas over here, well, these are not exactly linear, but you can make them linear. Like, see, if you add two lines, like over here, you can make an X. Here, it's perfectly linear. Now, let's just train our model with just two input nodes, because we have just two inputs, and output nodes are only two. Why? There are only two categories, blue category and orange category. So let's just train. It's a very clear there's a clear difference between these two categories. There's a clear boundary, and for that reason, in just 200 epochs, our model learned about this. Well, how about in this case? Oh god, it's taking forever. Well, this is not exactly a linear separation, right? We have to use two lines over here. So I'm considering it to be a non-linear. So I'll just, what did we learn in this particular thing? Okay, not in this one. Um, okay, wait a minute. Okay, nope, not in this one. Hmm, okay, I think an overfitting and underfitting. This particular thing I want you folks to remember. It's very important. Well, it'll help you make your own model. So now this thing clearly says that, okay, let's go to the definition of capacity first. A model's capacity refers to the size and complexity of the patterns it is able to learn. Here, in this case, it's fairly like it's a very simple problem. Like in even in a 100 epochs, a model with just two inputs and two outputs, it can learn. Whereas this thing is complicated one. It needs a higher capacity model, so it's not being able to learn well. It crossed over 500 epochs. In real time, training a model for like training a huge model for more than 50 or 100 epochs is a very tough task. It takes a lot of time. It takes hours to train it. So you can clearly see that something is wrong with your model. Let's just go back here. Okay, now I understand that I should increase its capacity. I have two options. I can make it wider or deeper. Now, I want to know, if I make it wider, how it will affect my outputs, and if I make it deeper, how it will affect my outputs. Now, I'll make it wider. Have If I add more units to the existing layers, then it makes it easier to learn more linear relationships. Okay, for linear relationships, I should keep the same architecture. I should just add more, like I should keep the sorry, same number of layers. I should just add some more uh, units. But for non-linear ones, I should add more layers. Okay, now let's go back to this simple model. Let's see. Okay, it's taking around 100. Enough for this. It's taking more than 100, right? Now I'll just add. If I just add one more neuron over here, it doesn't make any sense because, well, it's not a linear relationship. Like it's not a linear boundary. So I'll just add one more thing, one more hidden layer. Now, see, now at least I was able to differentiate. Like I have lost some of the blue ones, and I have, of course, considered these as red, like red ones. But I was able to partition these into three, into three regions. I made it into regions, but I want to fine tune these regions. So I want to make them like I have made a big partition. I want to adjust the boundaries of these partitions. So I'll just add one more neuron. I'm making it wider. In the earlier case, I made it deeper. Voila. In 200 epochs, it's clearly seeing that, okay, all these ones are the all these orange ones. Um, will be in this boundary only, and all the blue ones will be in this boundary by just adding one more layer. Without this thing, I was able to make, okay, now it remembers, as I've already ran this on my data, it is not remembering it. Okay, now this is a non-linear boundary. I'll just make it deeper. Okay, in the like in the previous example, all these blue ones were made into one region, and have one more regions, but the boundaries of these regions are not good enough for me. I'll just add one more node for creating multiple regions. Increase the layers, and to adjust the what do we say, boundaries of those regions, try to increase the number of neurons in that particular layer, make it wider. Well, that's it. Overfitting. And here we have already seen we can use neural networks for classification, right? But for making them into classification, like for using them into classification, we use this sigmoid function, or of course we can also use this tanh function. In this particular example, we have used activation function tanh. We can also use sigmoid. When you use tanh and sigmoid function, well, it's easier to classify. For example, if I've just used ReLU or linear function, I'll get some integer value. For example, I'm using for predicting stocks, or for predicting the sugar levels of a person by taking his um, blood pressure, or osmotic pressure in the blood and stuff. I can find out the sugar level value. That's an integer. But in classification task, when I want to categorize persons, I have to um, have not an integer value. I have to make a clear distinction, like that this belongs to this category. At that time, what we do is, here we have two groups. So our output layer will also have only two nodes, and each node will give a probability, saying that, for example, if I got a new data point, it's over here where my cursor is, it's in the orange region. Now it says that the probability of finding of this new data point being orange is 99%, and it being blue is 1%. Or it'll be like, not exactly in the percentage, it'll be like 0.99 and 0.01. Now adding these two will give you 1. That can be done using our sigmoid function. See, as you can see, this curve is in between 0 0.0 and 1. No matter what value you get out of your neuron, it will be mapped to between 0 0.0 and 1. In this way, we can get probability of an object, or of a data point belonging to a class, and higher the probability to that class it belongs to. That is what is in the last section of binary classification. Yeah, I forgot about dropout and batch normalization. These are important topics. Well, in our previous uh, like notebook, we have seen about overfitting and underfitting, right? Well, overfitting happens when our model completely remembers the data, but we don't want the model to remember our data. What can we do? What changes can we make in our model so that it doesn't remember? We can do something like this. Looks like discollage, but see, when my model is running for the first time on my data, it'll take one, two, three, first three nodes. It'll drop the last one, and in when second time it's running, it'll drop the first one, and it'll use the last three. So because it is dropping one of these neurons in a cycle, that neuron will not participate in that particular epoch, in that particular cycle. so it won't remember those values. If continuously I go through each and every book, like sorry, like how should I say, Hmm, okay, I want to learn how multiplication works, um, or else I want yeah, let's say I'm a team leader, and I'm going to participate in a competition. I'm still in my third class, and my team has 4 members. What I want to do is, my competition is, I have to remember tables between 2 to 10. What I'll do, I'll ask one of my teammate to remember second and third table. Like, I just want him to remember, I don't want him to what do we say, calculate them. I don't want him to understand the logic behind it. And I want my other friend to remember 4 5, the next one 6 7, and the next one 8 9. I'll remember the 10th one because it's easy. um, in the competition, because the competition is not according to my rules, what the judge decided is, he will randomly ask questions. What I thought, if there was a question about two table, I'll ask my teammate A to raise his hand and make him answer that. But now it's a randomized thing. My like judge will pick someone and ask them. So whatever I have remembered doesn't work. Let's say this judge scenario is our like a general state, our real time scenario. We don't know what might happen, what changes might occur. I can't just make my things, like make my students remember each and every table. So what I'll do, um, I'll make them learn in cycles. For example, um, I'll conduct series of tests. In the first test, I'll make my first three participants work, and then the next test I'll drop out one and I'll make the other three. So in this way, like whatever they have prepared that particular table, it will not be used. They have to learn everything, and they have to uh, work with, like they have to learn uh, to work with everyone. Now A have to work with BC in one round, and A also have to learn to work with C and D in the next round. Otherwise he will just learn how to work with B and C, and his coordination with D won't be good. In the same way, if I make all of these four at a time, these four will learn together, and they'll just remember the details. They won't actually learn. For that reason, we drop out them. And batch normalization is used to our input values. Okay, our batch normalization, what it does is, our input values may be of different parameters. It might be of like let's say blood pressure, osmotic pressure, weight, height. If I'm calculating in centimeters, it will be from 140 to 180 or 190. But weight will be from 40 to 100, 120. There's a scale difference. And if I take osmotic pressure, they will follow other units. Um, all And if I calculate the pH will be between 1 to 14. Normally human blood won't be that of varying of that range, maybe 5 to 9 or 10, in that range. Each scaling is different for each parameter. For that reason, we normalize them. We convert all these values between 0 and 1, such that their relationship with other values in that particular column won't be affected. So after dense layer, we use normalization to condense them. Okay, yeah, with this all introduction to these 6 steps are done. If you have any doubts, you can put them in the comment section. Well, for normalization, there is a min-max normalization. I, as far as I remember, we use the maximum and minimum value of that particular column to normalize, and we also use mean. I think normally we don't have to. Uh, yeah, in Scikit-learn there are standard scalar and min-max scalar, but in TensorFlow we can directly use batch norm. The inner working of batch norm, I'm not that sure about it. And yeah, of course I forgot. Dropout. How many nodes should we drop out in each thing? We can mention like with rate value, so that if I say 0.3, 30% of the neurons will not be used. Here I think it's 50%. Two neurons are being like are losing at the same time. If we mention 0.3, 30%. And I'll check different normalizations. Networks. Okay, there is this weight normalization and batch normalization. Okay, there's also Z score. In Z score, we subtract the mean value. Like it's a central value. Like we consider it to be the central value, right? We subtract the mean value and we divide it by our standard deviation. And there's also logarithmic normalization, and there's also clipping. Okay, in clipping, if there are values which are beyond the limits, we assign them values of those limits. Okay, here they gave about three. I think there's one more. Default we use batch normalization, and okay, log scaling, Z score. Yeah, that's it. Yeah, of course, linear scaling. We subtract the minimum value, and then whatever the difference is between max and min, we divide that above difference using this value. I'll just send this link to. And okay, Moise, did you like get your doubt clarified? And anyone else has any more doubts? Please feel free to ask. This is a beginner session. Even I'm a beginner. Okay, is neural network normalization layer different from conventional normalization? Well, um, as you can see, there are many normalization techniques, but in batch normalization, which one they particularly use, I'm not aware of that. I'll have to wait. Uh, okay, this is the okay Google's one. Um, Let me just check that. Not sure. Okay. Yeah. In batch normalization, they're taking that particular input and they are finding the difference between it and mean, and they're squaring it. Well, if you directly add it, if the difference is in two opposite directions, like in negative in negative x-axis and positive x-axis, they might just, what do you say, conflict each other and be zero. But that shouldn't be the case, right? Okay, wait a minute. No. This is the variance formula. And yeah. Hey, this is just this one, not this. Linear scaling. No, not linear scaling. A minute. Yeah, Z score. I think they're using Z score in batch normalization. Xi minus mean square root of variance. Variance is square root of variance is standard deviation. So yeah, they're using Z score. They're using Z score normalization in batch normalization, as far as I know, can understand. Um, okay, now is that clear? Should I drop that link too of batch normalization one? Okay, cool. Yeah, and any other doubts? Okay. Yeah, if anyone else has any more doubts, please feel free to ask. Well, for making your own models and working with them, a minute. There are two frameworks. There are more than two frameworks, but most of the personnel who are working with in this domain of machine learning and deep learning, or for beginners, Python is easy to use, and the frameworks in Python are TensorFlow and PyTorch. TensorFlow is from Google. Uh, Kaggle is also from Kaggle. Most of the okay, yeah, you can learn both PyTorch and TensorFlow. Well, that's it. Okay, then I'll be closing. I'll just wait for 2 minutes. If anyone doesn't comment, I'll just close it.